Okay, everybody, we're going to move on to the next session. Sorry about the brief delay. I'd like to introduce Kent Nebergall, who's going to talk about some risk reduction measures for long and deep space missions. So, thank you very much.
Okay, about here? Is that good? Not too loud, not too soft? Okay. All right. This is something I've been presenting several years in a row. It's basically, think of it almost like a periodic table of the various risks involved in getting into, starting with just getting into orbit in an affordable way, and then ending with space settlement. You'll notice that these are starting to get serious. We've got affordable launch. The Falcon Heavy is it's half the price and 3 times the payload that we're used to. We're getting into larger vehicles, mass fraction beyond Earth orbit or refueling on orbit. It's already done with the space station at room temperature, has been done for over a decade now. With low-level cryogens, that's what's you're going to see with the both SpaceX's system and Blue Origin's in the long run. But what we have here is sort of a box of things that are not really being addressed. Health effects of being in deep space in terms of solar flares, galactic cosmic rays, and cell damage. Medication tends to expire faster. Food's nutritional efficacy, nutritional value tends to expire, vitamins, minerals, and so forth in the deep space environment. We know this from low Earth orbit. It's going to be double in deep space. And then also various diseases that affect the human body tend to get even more virulent in microgravity. So you have a decline in the effectiveness of our medication and an increase in the virulence of the diseases. So is that going to have a crossover where we end up coming home sick? So that's the medical entropy and so forth. So what we're trying to do is get rid of this box so that we can break out of this and get onto the rest of things. Meanwhile, we also have, and this is the topic of my next talk, right after this one next door, is we're going to have a technology revolution in the next few years because we have a convergence of a number of items coming along in approximately the same coincident time. So we have Falcon Heavy, we have New Glenn. NASA is doing some interesting things with nuclear power. I'll show you briefly. This low latency constellation is going to help pay for a lot of this stuff. Bigelow Aerospace is talking about 2020. We've got other things like blockchain and AI and so forth that will also be sort of mixed into this and will help superpower it a bit. And then, Falcon 9, Block 5, Crew Dragon. We've got a lot of things in this spectrum. NASA is starting to get serious about nuclear power on the surface. This is all 3 of these use low enriched uranium, so they're relatively safe to use. The other advantage of this is that because it's not burning very fast, it burns for decades without a lot of overhead. So this is a bunch of basically Stirling cycle motors around uranium core. This is a larger version of the same thing, but we're starting to get into the power ranges we need for Mars Direct. And they're also working on this is only about 25% more efficient than a regular engine, but it's a nuclear engine. It's a NERVA. It's just using low enriched uranium. So what can we do to get out of that box, as I mentioned? Well, here's one idea, is we take a Dragon on a Falcon Heavy and we put it into an extremely long orbit, approximately similar to the one being used for the idea of sending 2 tourists past the moon on that mission in 2020, 2021, somewhere in there. We do the same thing, except we load it with a bunch of long duration exposure payloads, just very simple ones. We'll get to that in a moment. And we expose it to full unfiltered cosmic rays, solar flares. We can kind of simulate the effect of a solar flare just by passing through the Van Allen radiation belts periodically. It takes relatively low delta V to get up into this orbit, and then all we need to do to get back from that orbit is just give a little kick here, and then we come right into the atmosphere. And we're coming in at roughly the speeds we would if we were coming back from Mars. So we can load it with food that we would use on a Mars mission, and we can see what the radiation degradation is. We can do the same thing with medication, with vitamins. We can put pathogens in samples to see what see if they become more virulent in that environment. We can also take seeds that we would grow for food in a complete nutritional system to get an idea of how are those going to become sterilized at a particular rate over a 3-year period. And then we could even take samples of our own gut bacteria, which we need to process food to begin with, and put them in this. It's not going to be exactly the same environment because there's not going to be a human there to encapsulate them, but it's not a bad idea to see what the effect is on that part of our digestive system that we are so dependent upon. And the nice thing about all these things is they're itty bitty. We can pack a whole bunch of this science in one Dragon capsule. So one of the things we've seen with the space station is we've finally gotten to the point where bone decalcification and muscle loss through a combination of diet, exercise, and medication, those can be that 1% per month of bone loss that we were dealing with is finally arrested. That's why we were able to do the 1-year missions to the ISS and see if that persists beyond 6 months like we've been doing. The thing we're having a problem with is ocular changes. About 1/3 of astronauts come back with roughly the same vision. 2/3 are having visual distortion on orbit, and it still lingers after they get back, and it doesn't necessarily quite go all the way to normal. And the problem is that basically fluids from the spinal column and so forth are kind of working their way into the optic nerve and distorting things a bit. So it doesn't affect everyone. I mean, you might be able to screen somebody with an MRI and say you're going and you're not, but it's bad enough that, you know, we don't know about this. So we know this is an issue in microgravity, but we don't know about the range beyond that. So what we could do is we could make a spinning laboratory that checks at all these different gravity levels. This is what Greg Binford mentioned this morning is going to be a topic of the plenary tomorrow morning. And that guy apparently is thinking almost exactly as I am. But if there's any issues at Earth gravity in this spinning lab, then we know it's due to radiation, because some of the damage to the cells that make our bones, we don't know if it's radiation or microgravity, because you're exposed to both on orbit. So I nicknamed this, well, here we go. So if you took a Dragon lab and you took a framework and you extended it out of the trunk, you've got a great place here to stick this thing, and connected it to its own second stage and started spinning it. And this would be a simple framework. It wouldn't necessarily have the full load. What you'd have is like 4 tethers around the corners of it, and then you'd be able to automatically adjust the tension in those tethers while using the framework as a compression element and the tethers as a tension element, because you can load a lot more weight on a rope than you can on a bar. So the beauty of that arrangement is that if there's any kind of oscillation or shimmy in there, you could have the tensioners and so forth automatically zone it out, zero it down. That way you don't have the possibility of it falling apart like a bridge and so forth. And there's a company called Made in Space that's already working on the idea of building a framework like this in space that's able to connect data and power all the way through the frame. The spin rates at 100 meters are relatively tame, 1.8 for the moon, 4.5 for Earth. And if we wanted to do a crew version, we would dock a Dragon onto the end of a BA-330. We would also have a fuel transfer module back here at the back end. As we added more stuff to this end, each of these Falcon second stages are approximately 2.5 tons. So we would basically add enough of these to offset the weight of this. We would also be fueling up either the stages themselves or a core stage specifically for this purpose. We'd get this outfitted up and then launch it into either that same trajectory or wherever, and spin it up and be able to have a laboratory like that. And this addresses, ULA is working on some stuff with fuel transfer. All these are essentially the challenges we were talking about. These are programs that are already in this zone. So it doesn't necessarily have to be these elements. I mean, ULA could do it, Bigelow, SpaceX. NASA Langley has some stuff on frame structures and so forth. There's a lot of programs that are in this space that could utilize a mission like this. And these are, you could have microgravity, just leave it in, just don't spin it. Lunar gravity, Mars gravity, and then put enough fuel back here and you've got either a Mars flyby mission, you could go out to the Lagrange points, whatever. Comparison of the Deep Space Gateway, the Can we do microgravity? Can we do deep space exposure? Yes. Microgravity, yes. Artificial gravity, we can. Sample return time. One of the critical things is how long does it take to get from the lab on space to the lab on Earth. In the case of a deep space gateway, it's going to take 4 days to get it from the deep space gateway all the way back to Earth in an Orion capsule. In this case, all you're really doing is you can take it out of the lab just before that encounter with Earth when you get in the Dragon and come home. So you've only got a delay of a few hours then. Or in the case of just this basic one, you just, when you snap off the capsule, you're doing lab work pretty much all the way until you safe it on the way into the atmosphere. Cubic volume, if we take this module and this module, you're at 139 cubic meters, but we're at 330 on the Bigelow habitat. We're only at 10 meters on a Dragon, but that's not crewed at this point. Mission cost, this is $8 billion for Deep Space Gateway approximately, based on the cost of the individual missions to build it and the modules from the space station that they're doing. They haven't given a cost estimate on this yet, but so this is at bare minimum price. These are published figures from SpaceX and Bigelow and so forth. So this price does not include the $7.7 billion we've already spent on SLS or the $11 billion we've already spent on Orion. So we could build all three of these. We could build an Earth, Mars, and lunar versions of this and a microgravity version and still have $2 billion left over for the price of this vehicle that's half the size of one of them. So when Elon Musk announced this last year, everybody thought, wow, that's great, but it's awfully big to do as the very next step. And he's announced recently that he's going from a 12-meter diameter to a 9-meter diameter. And the question we had before that, when I was discussing this with Kevin Hemsch was a guy I was working with on some of these projects, was how could you shrink the ITS design all the way down to fit it on a Falcon? So what's interesting about this is if we take this and we shrink it down to a 9-meter diameter, we lose 25% of the diameter, but we lose 70% of the volume for the propellant and for the crew. So this doesn't look that much smaller, but it is a way smaller. You go from almost 2,000 tons to 576 metric tons of propellant. That's a dramatic impact on the mission. So you've noticed that when he announced this, he also said, well, we're thinking about moon bases now. This is more of a moon vehicle. It can do a crew to Mars. I mean, this was beyond our wildest imaginations for Mars Direct. This is one great vehicle for that sort of crew of 10 or fewer. It's not a 100-person colony ship, but it's still a pretty darn good ship. If we take it all the way down to something that can fit on a Falcon Heavy, a Falcon, this is only 72 tons. We get more than twice that for a Falcon Heavy. So what could we do with these little tiny guys? This thing is so tiny it could barely reach the space station. But the advantage of it is you have a fully reusable second stage trunk and Dragon capsule in one bundle. So it actually might make sense to do something like this. For this guy, we could get a much larger weight capacity up to the space station, more than double what we could do on that one. However, if we could get this all the way down to 13.5 metric tons and refuel it on orbit, it would just barely make it to Mars. So not a bad prototype. It's not a very practical mission because it wouldn't necessarily be able to get back. It's probably good for robot. It would be a great atmospheric entry demonstrator to reduce the risk even further than the 9-meter version, because the 9-meter version is still a pretty heavy vehicle. But they could do this as a demonstrator. These numbers are very, very napkin sketch because SpaceX is very loath to announce a lot of the details of these things. I'm not getting into details on the 9-meter because Elon Musk will be doing that himself in a few weeks. So there was no point in doing the math on that. Then as far as these, what do we do as a group going forward? We have our list of grand challenges. Some of these are science problems. We need to know what we need to know in order to design properly. Some of these are engineering problems. we have certain things that are known answers. I'm putting together a web page where I'm trying to compile all the research I can on these things and in this sort of schema. Where we have other situations, we suggest doing more research. Some expensive R&D, obviously, you can't do on a napkin sketch. So we can find and suggest solutions, which is what I've been doing for the last 15 minutes. And then lastly, if it's cheap enough, we may be able to create our own solutions going forward. So that's all my main information. If you like more stuff, there's my website and my contact information. And we have time for a few questions? Okay. Thank you. Yes?
Yeah. Gertie was only a problem because there were winds that were strumming it like a guitar and making so I can't see how, especially if you put some kind of shock absorber on a tether, why that would give any risk. There's nothing that's going to strum it and make it.
It's literally a belt and suspenders approach. I mean, if you get, especially if you got a crew walking around, you may have more of an issue with it. If you fire the engines, whatever. They did an interesting experiment on the shuttle where they just physically built a huge tower off the end of it, or extended a platform for a radar, and they had jets on the end of the platform and obviously the rockets on the shuttle, and they had to constantly dampen for it. If you had an active dampening system using cables, you're not burning any propellant. So you may be able to, you have oscillations that you do have to dampen anytime you move it, because they're not going to move at exactly the same rate. You're going to have a bowing effect.
If you use very low thrust, then you should really build up. And also,
Again, this is just, let's be as safe as humanly possible with this sort of design. It's probably overkill. That would be great, because then we could make a much longer tether. Any other questions? Yes?
What do you perceive as being the major single obstacle to the program of developing a viable mission to Mars from a technological?
Technologically, part of the issue is that we have these challenges, and we're slowly working our way into knowing the science of how to deal with them, but we're not doing it quickly enough to do it, in a reasonable amount of time. So we have this wave of affordable launch, and we have this buffer of things we need to know in a hurry. We're learning a lot of them on the space station. We've made great strides on the space station. It's been beautiful, but we need to triple that. And some of these things are just very simple. They just can't be done in low Earth orbit. They have to be done in deep space.
there are some capsules, or some payloads that have been significantly wider than the core that launches it. So you're not really limited by quite as much as you might think by the diameter of the Falcon.
Well, this is the same width as I tried to keep this the same width as this, just to keep it safe. So any more? Okay, great. I'll be next door, and Art will be picking up here in a moment.